In this first part of the activity, you'll need all those nice red and white water molecules. And you notice you don't have to cut them out exactly. If you leave a little white, it makes the cutting go a lot faster. Okay, so you'll need them spread out like this. And then what I want you to do is think about the fact that they're polar and they have a negative side and a more positive side. Each one, you'll notice it's marked on here. There's little minuses here, and there's a plus and a plus there. And you'll remember that's because the electrons are spending more time going around the oxygen because it has 8 protons. And then these poor little protons up at the top, they don't get the electrons very much. So all the negative electrons are hanging out down here, making this negative. This is positive. So what's going to happen here? Positive and negative opposite charges attract. Positive and negative want to be together, and the same kind, like 2 positives or 2 negatives, like charges, repel. So if you try to put these together like this, a negative side and a negative side, it's going to go like that. They're not going to want to go together. So how are these all going to interact? See if you can sort of move them around and line up. Let's see, I think maybe positive and negative would want to go together. So what happens to this one? So pause the video and take a few minutes and play around with them and see if you can figure out an arrangement. There's no one right answer, okay? So see if you can figure out an arrangement where the most number of molecules are happy with the arrangement. Okay, so here's one way you could arrange them. I have it looking kind of random. Yours may look more structured, but I've just made sure that a positive and a negative side are close together. They're going to be happy. This one wants to be with that one. This one here, 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 and here, here. And this one would be, see, these aren't real happy, so it kind of is a turn. This one is kind of awkward. See, this one's kind of attracted to this and this and this all at the same time. And here, okay, and this one maybe is like attracted to here, so I'm going to turn him a little bit more. Okay, so they're moving around though. So remember, oh, this arrangement, you might get something really nice, but they're moving, swirling around, and they're all going to be finding new ways to attract and arrange themselves constantly. Here's a fun little molecule building set that I purchased from Carolina Biological. If you want to buy one, they're kind of expensive. Just this many molecules is like $50. But if you'd like to own one, you can go to Carolina Biological. Just Google it. I think it's carolina.com online, and you can find it there. And you may be able to get some other places too. It's looks like this 3D water kit. Right? And what they've done is they've put magnets inside these little water molecules so that one of them, north or south, I don't know which is it, is in these are the same, and then this has another pole. So what will happen is that the red and the white will be attracted like that. Okay. So if you try to put these together, they're going to repel. They don't stick. So the positive and negative, this is to simulate this hydrogen bonding that goes on between the water molecules. So if we kind of mix them up, they'll kind of like fall into place. So that's maybe what water molecules would do. Right? And then I'd mix them up. This is a lot easier than moving my paper around, right? But the molecules decide where they want to go. And they would automatically kind of go like that. It's kind of neat. In plants, you get this thing going on where you get kind of a line. Transpiration is where the water goes from the roots up to the leaves. And I like to imagine it as a kind of a continuous line of water molecules attracting each other. Let's see, how would that be? That would go on like this, right? So you get the you get the water evaporating out the top end, and it pulls. This one leaves and this one goes up, and each one pulls on the one below it, and it pulls the whole line of water molecules up. This is also what creates surface tension. You have a drop of water there, it can stay round, right? So that's what lets water heap up into a droplet. If you put it on a nice waxy shiny surface, the droplet will be fairly round, and this is what allows it to do that. It's this attraction of the water molecules for each other. So this is how you might indicate this if you were making a drawing and you wanted to show that there was some attraction going on. You would just make a dashed line. Let's see, between here, there's traction going like this, right? And between here, and between here, and here, here, not between here, so I won't draw one, here, here. Okay, so not this, maybe I'll swivel this one around like this. So I can draw a traction here and then here, like this. So this is how you would indicate hydrogen bonding, these really weak forces that keep it together. You just make little dashed lines. This is a really cool computer-generated graphic here showing our space filling model, right, of water. And it kind of is nice because it really looks 3D, doesn't it? They're all turned differently. And you can see the dotted lines here. This one's attracting that one, and that one's that one. It gives you a real good idea of what's going on in space. Maybe this one isn't being attracted by any for a split second, but then it'll turn, and a split second later it'll flip, and maybe it'll be attracted to that one. It also lets you see our little squiggly line things here. See that? Okay, so when you see one of those, don't freak out, remain calm, and it'll have a plus or a minus by it, and that tells you that the overall charge here is plus, and the overall charge here is plus, and the overall charge on this side is minus. Okay, so that's all that it means, but there's that little squiggle that we drew. So I just thought you'd really like to see this. It's a really nice picture of how all the water molecules are interacting with their hydrogen bonding. So here is an idealized structure for hydrogen bonding. If the water molecules were sitting still and they could line themselves up perfectly, they might do something like this. And perhaps you discovered this in your arrangement, maybe use something that kind of looked like this, which theoretically would work. The only problem is they're moving all the time, and so these guys would be constantly shifting, and you never would really be able to achieve something like this because they're in motion all the time, and they're three-dimensional. This works nicely in flat. However, the molecule is in 3D, and the water droplet is three-dimensional. So you get molecules here and here, oh, close, far away. Okay, this is trying to show you that it's got depth. The picture goes like that too, right? So this is kind of the far away molecule. So you'll notice here, though, the dashed lines, right? Those represent the attraction here between the red side, this would be the negative, and the positive over here. So it kind of gets complicated when you see it in 3D. So although you may have discovered something like this works really well, the reason you don't really have that is because the molecules are 3D and they're in constant motion. But the most important thing to remember is that they are polar, they attract each other, and that you use dashed lines. If you want to write it down, use dashed lines to represent hydrogen bonding. For the second part of the activity, you'll need this crystal with all the NaCl's, and you also need some individual ones cut out as well. Okay, so this is a salt crystal. Now, when we say salt, we're assuming it's table salt, sodium chloride, NaCl. There's different kinds of salts. You can have KCl, and anyways, the definition of salt is pretty broad, and so this is a very idealized salt. But this is, when we think of salt like we put on our food. We're usually thinking about sodium chloride. Na is sodium, Cl is chlorine. And once again, what are these? Well, they are elements on the periodic table. And over here we have sodium, number 11, and way over here is chlorine, number 17. Now the neat thing about sodium chloride is chlorine over here has 7 in its outer shell. Remember we talked about the octet rule. It has 7, would like to gain 1, and all these guys over here, which sodium is one of, have 1 extra. So this is a perfect match. This column here says they'd like to get an extra, and this column here says I've got an extra to give, and very often we find that we have matches from opposite ends of the table. And this is exactly what happens with sodium chloride. They get together, and they actually, this isn't covalent though, this is ionic. They actually kind of transfer their electron over. It's not a sharing situation, but that's for a chemistry class. We don't need to go into it any deeper than that right now. What we need to do is get some of these waters out here. Put them around here and see what happens. Okay, they call water the universal solvent because it dissolves things. Let's see if it can dissolve the salt crystal. Okay, for example, right here we've got chlorine, which is negative. So the positive side is going to be attracted, isn't it? Like this, negative, positive, like that. And see down here we've got Na, sodium, plus. So it's going to be attracted to the negative side of the water molecule. Okay, and you can do that with yours. You can do it after I'm done, or you can do it while you're watching. Again, over here we have positive and negatives lining up, and the water is actually going to pull. These waters are going to tug on the crystal and pull them off, pull them apart, like this. Then this one's going to pull that one off, so this will go floating away. Right here's this one, there. And let's say this one pulls the chlorine off here, that chlorine pulls it away like this. It's going to start disassembling this. Let's say that one was in there like this. It's going to start pulling them away until there's nothing left, and all you have is a bunch of these things floating around. The crystal will break up into individual atoms. Now, let's see. We got this guy attracting here and this guy attracting here. Okay, so what's to stop this guy and this guy? Look at this, plus and minus going over like this and sticking together. See, this is positive, this is negative. Why not just go like that? Okay, see if you can take all your waters and make an arrangement where you can isolate. You do not want the sodium and the chlorine getting together again, because then it would just form a crystal again, right? We don't want that. We want it to stay dissolved. Stop the video, pause it, and see if you can move the molecules around to see if you can insulate to keep the sodiums and the chlorines apart. Okay, did you come up with something like this? If you surround the sodiums with all the negative sides like that, you can make like little cages around. Maybe there might even be another one on here. Maybe there doesn't have to be 4 or whatever. But you need to make little protective cages. Now, I know these things are next to each other and you're going to say, oh, they don't like each other. But it works out in reality in 3 dimensions. And so these guys are just going to have to put up with it. The attraction here is strong enough that these guys are just going to have to just shut up and live with it. So this is what, in fact, happens. The water molecules turn so that their, in this case, positive side is facing the negative chlorine, or their negative side is facing the positive sodium. And this is how it keeps the molecules in little cages. And this is this is what happens when salt dissolves. This is what it means to dissolve something. You break it up into little tiny pieces, and these little pieces go floating around in the water. But the water acts as little cages to keep these insulated by themselves, which is actually a good thing too, because both of these things are very toxic on their own. If you had pure chlorine, if we had like green dots, just a whole page of chlorines, that's really nasty. I mean, you put chlorine in your swimming pool to kill microorganisms, right? It kills microlife. It's poison. And in fact it is, and in its gaseous form it's a green gas, and it's really, really nasty. It'll kill you. So this is very dangerous, and this is too on its own. But as long as they're isolated, put in little water cages, everything's okay. And the interesting thing is that these are actually very important to your body. The sodium, chlorine, and other ions, potassium and other things as well, are very necessary to especially your nervous system to be able to generate electricity in your neurons. So it's good to be able to have these in your body. You need to use them, but we got to keep them safe. So this is the built-in safety feature. So you can get all the good benefits of these without the downsides, thanks to water, the hero of the day. Here's a quick little bonus demo using my little 3D water kit here. In the kit they give you a blue ball and a green ball. And of course it's kind of color-coded, same way we color-coded: sodium, blue, chlorine, green. And the reason they usually use green, whoops, yeah, they do stick together. Chlorine, just by itself, if you have nothing but chlorine atoms, it's a green gas. It's poisonous green gas. So anyway, there is a reason chlorine really can be green. There's a reason to make it green. And sodium is not blue. Sodium is a silver metal, but I don't know, it's just kind of standard to make it blue. Okay, so what happens when we'll do sodium first. Rolling around here, trying to be dangerous. We have, so this is the, right, the negative end, the red side. We have these negatives sticking on, and they've given us, I think it's 6 little magnet sites here that can stick on. So we made our cages two-dimensional. We just kind of had a flat diagram. But you remember the cages are 3D. And of course you'd still have them sticking like this too. So really, you could have the atom be pretty buried like that. Okay, and then the opposite with the chlorine. We'll switch it out for the green, and that would stick with the whites. Right, so we're going to make something like this. It's a little more spacious in there. Okay, and then of course you'd still have them like there. Okay, so that's going to stick like that. You see how they kind of figure out how to arrange themselves somehow or other? Okay, that one's going to stick like that. They kind of decide how they feel comfortable. So you end up with something like that. So you'd have, if we had a whole bunch of these, clump, 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 and then we have green and blue balls buried in them, and that would represent salt water. This is part 3, where we're going to look at some other polar substances that will dissolve in water. So you'll need these little molecules. Okay, and at this point you're going to be thinking, wait a second, I'm enrolled in the wrong course here. I wanted anatomy and physiology. This is chemistry. So hang with us, we'll get to anatomy and physiology. But the body is basically a bunch of chemicals. And so understanding the chemistry is very, very important to physiology. Okay, so let's look at this one. This, you see there's hydrogen and there's chlorine. This is hydrogen chloride, but it's very often called hydrochloric acid. When this is in a solution, it's called hydrochloric acid, and technically HCl is hydrogen chloride, but it very often gets called hydrochloric acid. And this is a substance made by your stomach. you have little cells in the lining of your stomach that make this. This is an acid, hydrochloric acid, and it helps you to digest your the proteins in your stomach. Helps your digestive enzymes. So this is actually a body substance. So there we go. See, got some anatomy and physiology in there. Okay, this is not a body substance. This is, you see sodium, and there's the hydroxide ion right there, right? So this is sodium hydroxide. This is a white powdery substance that they used to get it from something called potash. If you've ever heard of lye, L-Y-E, not L-I-E, but L-Y-E, like this, lye. It's a old-fashioned soap, L-Y-E. They used to use that to wash, and now lye still exists, but we've refined soap making technology, and we don't use just plain lye. They would probably use that in the soaps, but along with other things. So this is basically a very something that gets used a lot in cleaning products. This is an acid, this is a base. These are very opposite. Now they're equally nasty, but this is alkaline, very, very basic. Okay, so let's look at the electrons and what's going on here. Chlorine has 7 in its outer shell. There's its 1, 2, 3, 4, 5, 6, 7. And we know that hydrogen has 1, and chlorine would like to have 8. So these guys are going to share to make 2, 4, 6, 8. And this is as similar as we saw in the water molecule, right? Hydrogen is always willing to donate its electron to somebody else. And that leaves the proton pretty much by itself, right? Because look at this. This is a big atom here, and they're all whizzing around. These 8 are like on their little 8-person carousel going around here, right? And this poor proton, and chlorine has a larger nucleus, so they're very attracted down here. So we're going to have a positive side with the poor little proton sitting here. It's nothing more than a proton, like that. I'll zoom in a little bit. Nothing more than a poor little proton once the electron leaves. So this side's going to be positive, and this side's going to be more negative. You can see where there's already a negative sign there. It's a dead giveaway, right, for the chlorine. So it's a little more complicated with this one. We've got 3 atoms joining up, but we can see here, all right, 2, 4, so oxygen has 6, 1, 2, 3, 4, 5, 6. It wants 2 more, gets 1 from the hydrogen. That's the scenario we're used to. So the poor little proton is left all by itself, lonely. Once in a while the electron comes and whizzes around. Hey, I still love you, you know, but kind of goes back to its party. Okay, so the sodium is very much like hydrogen in that it has 1 extra in its outer shell. It's bigger, it's got a couple inner shells, but it's got 1 that it's very willing to donate. And so it does that a lot. So then the oxygen's happy, all the electrons are happy. Remember, electrons like to be in pairs. These were happy, and these were happy. Now this guy's happy, and this guy's happy, because they all have little happy couples. But this makes this positive. This electron leaves, and now we're kind of heavy on the protons over here. So this side's going to be more negative right here, right, with these electrons. This is going to be more negative, and this is going to be this is going to be positive, and this is going to be more positive. So we still kind of have a lopsided molecule. Now, like everything we've looked at is like lopsided so far, and you're going to think, oh, well, all molecules are like this, right? Okay, no, they're not. And in lesson 2, we're going to see some that are very evenly balanced, and we're not going to see this kind of lopsided electron scenario at all. So hang in there. Right now, the world is full of polar substances. Okay, so what I want you to do is pause the video just a second here and get out these guys. What happens when water comes into the solution? Okay, bring out your waters like this. What is going to happen? they're going to start tugging, aren't they? Let's see, that's the positive side. It's going to start tugging on this. This is going to start tugging. Okay, this is the negative side is going to start tugging on here. Water has the ability to pull. You know, you got these guys on this side pulling this way, and this guy's is attracting this way, and they're attracting like that. Okay, so what's going to happen is they're going to get pulled apart. So you can add in like these guys, these extra ions and things like over here. So what I want you to do is, let's pretend that these have split up. So we have individual ions and a bunch of water molecules, and see if you can arrange them in a way that might be a plausible scenario. Okay, once again, there's no right answer. There's no one right way to arrange these. The main point is that we have taken this and broken it up till we have a chlorine, and there's my little hydrogen ion or proton. It looks like a proton, doesn't it? Because it's got that plus. So I call it a proton there. Okay, that's what happened to that. And what happens to chlorine, right? I put a little cage around it. So that's what happens when it dissolves from the salt. So I assume that would be the same thing what happened here. These positive sides of the water molecules are going to be attracted to the negative chlorine. You might get this little cage here. Now, does this guy need a cage? I mean, you might have some attraction here, like that. You know, maybe you're going to form hydronium for a split second. But remember, these guys are floating around in water. Yeah, he might go and he might attach like that, and then immediately this one will split off and go or something. But these guys, the H's, the hydrogen ions, H pluses, and the OHs, they just float around, right? They don't need a cage, okay? So down here we have the sodium I took off here. Put the sodium here, and then we have the hydroxide ion. So you're getting used to that already, right? Hydroxide ion, you don't freak out when you hear that. So the more you work with it, the more you learn it. There's the hydroxide ion right here. Okay, and he doesn't really need a cage. I put a cage around this guy, right, because that's what we did with the salt. And this one right, this guy and this guy, they float around, and they might actually find each other, right? What would happen? They'd make a water, so they might find each other. Okay, so H's and OH's do float around a bit. If there's a whole lot of these things, many, many, many more of these, the substance will be an acid. If there's a whole lot more of these, not so many of these, and a whole lot of these, the substance will be alkaline. It will be basic, a base. Okay, I'm just about to evaporate my last molecules. These were going out like this, and I was just left with these, which would find each other and go off, right? The hydroxide and the hydrogen ion would find each other and make water. They could go off. And what am I left with? It looks to me like sodium chloride, right? It looks like a very tiny, tiny salt crystal, right? There'd be a lot more of these, and even a very small salt crystal. But what we're left with is salt crystal. So kind of strange, but if you take hydrochloric acid and sodium hydroxide, if you're doing a little chemistry experiment, and you take this terrible acid and you mix it with this nasty white powder that comes, it's like a laundry soap or like a soapy powder, and you mix it with this hydrochloric acid, and what you're left with, what's going to happen, these things are going to pop off. This is going to go here, this is going to go here, and these, we're going to get some waters, these will go here. So what you're going to be left with is salt water, basically, right? You can combine these two things, mix them up, and be left with salt water. So if these evaporated out, you'd just be left with a salt crystal. Now what's going to happen? Can we reverse the process if we want to go back and get these again? This is like this soapy powder, and this is this very specialized acid in your stomach. What will happen? You can say, hey, let's reverse that. Let's go back. Let's add all the water again. Hey, let's add water and see if we can get those interesting chemicals back again. Is this going to work? We did this scenario, didn't we? We dissolved this, and what do we get? We just get these in cages. We did not make nifty chemicals. We just had these things dissolved in the water. So this is a one-way chemical reaction here. These can make this, but we can't go backwards. We can't get these back again. So, too bad, right? Now, one little neat thing, a little trick you can do with this. Okay, this sodium hydroxide is an ingredient found in a lot of cleaning products, and maybe like laundry soap or whatever. They used to use lye to do a lot of wash clothes and stuff. So something like this or something like this is probably in your laundry soap. If you have like a dry white powdered laundry soap. The interesting thing is when this happens, when we dissolve this in water, the process of taking this apart releases energy, and it's kind of neat. If you take some of the dry soap, put it in your hand, put a little water on it, it'll get hot. And you'll feel that heat. You'll feel heat. And then as you continue to mush it around, it'll start to feel slippery. And that is a feature of alkaline substances. They feel slippery. That's why soap feels slippery. And if you were to taste it, it would taste bitter. So that's what alkaline substances do. They are slippery and they taste bitter. So anyways, that's a little thing you might want to, little bonus activity there. You might want to run down, and if you have some white powdered laundry soap, put a little bit in your hand, put some water, and you can feel the heat